Contact.
Contact.
A pilot is expected to manipulate the engine controls to A. Create the desired amount of thrust, B. As efficiently as possible, and C. Without damaging anything. To accomplish this, you need to know how engines and propellers work. You need to know how to interpret the information from your engine-related sensors. And you need to know what each of the engine controls available to you does. Our discussion of airplane piston engines will begin with a description of what happens during each of the 4 strokes of a 4-stroke engine. Then we'll discuss various subsystems of the engine one by one. The induction system is responsible for making sure that the correct amount of air and the correct amount of fuel get into each cylinder. The ignition system is responsible for making sure that the fuel and air mixture in each cylinder starts burning at the correct time. The exhaust system is responsible for routing the burned mixture away from the cylinders and avoiding the noise that may be generated by that. The lubrication system makes sure that parts which rub against one another do not wear out prematurely. The cooling system keeps the engine cylinders from getting too hot. And finally, the propeller turns the rotation of the crankshaft into thrust. This diagram is a schematic cross-section of one cylinder. The purple part is the piston. The piston is connected to the red crankshaft by a connecting rod. I haven't shown the connecting rod because it was difficult to animate that correctly. During the induction stroke, the piston moves down, which draws the mixture of fuel and air from the induction manifold. The intake valve is open during that stroke, but the exhaust valve is closed. During the compression stroke, both valves are closed. Upward movement of the piston compresses the fuel and air mixture. The spark plug ignites the fuel and air mixture just before the end of the compression stroke. It takes some time for the mixture to burn, so the mixture should all be burned by early in the power stroke. Burning the fuel greatly increases the pressure inside the cylinder. This pushes down the piston. Both valves are closed during the power stroke. During the exhaust stroke, the exhaust valve is opened. The piston moves upward, pushing the burned mixture out into the exhaust manifold. Each cylinder is only producing power for 1/4 of the time. However, most aviation engines have 4 or more cylinders. The strokes of the cylinders are interleaved so that the power is close to continuous. Airplane engines typically have multiple cylinders connected to one crankshaft. There are several different ways to arrange the cylinders. The horizontally opposed cylinder configuration is the most common in modern general aviation airplanes. Radial engines were common in World War II era airplanes, and you may encounter some other cylinder configurations such as inline engines. These pictures of a cutaway engine show the crankshaft and the camshaft. The pistons are attached to the crankshaft by connecting rods so that the pistons move up and down as the crankshaft rotates. Cams on the camshaft open the valves at the correct times through a mechanism with push rods and rockers. The camshaft is driven by the crankshaft via gears at one end of the engine, as shown on the left. Since the valves open once for every 2 rotations of the crankshaft, the camshaft rotates at half the speed of the crankshaft. This picture of the cutaway engine shows two of the four cylinder assemblies. This is what a valve looks like. The push rods are housed inside push rod tubes. The push rods are linked to the valves by rocker assemblies. The rocker assemblies are not visible here because they're enclosed by a rocker cover. Each cylinder has cooling fins to dissipate the heat. A little bit of one of the pistons is visible in this picture. And these holes are where the spark plug will be inserted.
So we move the throttle when we want to change how much power we are getting from the engine. I've seen you moving those other levers next to the throttle sometimes also. What do they do?
The other two controls on our throttle quadrant are the mixture control and the carb heat control. Those are part of the engine's induction system.
This figure illustrates a carburetor induction system. We'll discuss fuel injection later. In some aircraft, the air flows upward through the carburetor, as shown here. In other aircraft, the air may flow downward. The induction system introduces a mixture of air and fuel into the cylinders. We want to control the amount of air-fuel mixture entering the cylinders, and we want to control the ratio of fuel to air in that mixture. When the cylinder draws in air during the intake stroke, the pressure in the intake manifold is reduced. In a normally aspirated engine, air gets pushed into that intake manifold through the carburetor by atmospheric pressure. Air pressure decreases with altitude, so it's less effective at pushing air through the carburetor into the engine as the airplane climbs. Since less air flows into the engine, the engine will develop less power at higher altitudes. The throttle restricts the flow of air into the intake manifold so that the pilot can adjust the amount of power that's produced. We tend to think of the throttle as making the engine develop more power, but what it's actually doing is it's preventing the engine from producing more power than we want. The throttle is the primary control for adjusting engine power. Other engine controls like the mixture control and the carburetor heat control will impact the power output as secondary effects. If the aircraft has a fixed pitch propeller, then the tachometer, which measures the crankshaft speed, will be the primary instrument for measuring power output. If the aircraft has a constant speed propeller, then the engine speed is set with the propeller control, so we needed something else to measure power output. That something else is a manifold pressure gauge that tells us the pressure of air in the intake manifold. A turbocharger pumps air into the manifold as opposed to relying on atmospheric pressure. Pumping the air requires some power. A turbocharger is powered by a turbine in the exhaust system. Some turbocharging systems are designed to increase the engine power at sea level. Others, which we refer to as turbo-normalized, just prevent that degradation that would normally happen with altitude. A wastegate diverts exhaust around the turbine to prevent it from doing more boosting than desired. In some aircraft, the pilot has to control the wastegate. In other airplanes, the wastegate is automatic. Carburetors add fuel into that intake air upstream of the throttle. The amount of fuel varies almost proportionally with the volume flow rate of air. So when you change the throttle setting, that doesn't appreciably change the fuel to air ratio. Although the amount of fuel varies somewhat with air density, it's not proportional. Therefore, the mixture tends to get richer as the aircraft climbs. Most aircraft carburetors have a mixture control which allows the pilot to change the amount of fuel being added to the air. Some engines, like the Rotax 912 series, have an altitude compensator that changes the amount of fuel being injected, and that may replace the pilot-controlled mixture control in those aircraft. Setting the mixture control is a complex topic, so I've decided to cover that in a lesson of its own. Once that lesson gets posted, I will post a link to that lesson here. Most aircraft carburetors are float-type carburetors. In that type of carburetor, there's a chamber that's partially filled with fuel up to a specific level. A float inside the chamber opens a valve whenever the fuel is below that specified level. The fuel jet is close to the same level as the fuel in the chamber. It has to be just a little bit lower so that fuel doesn't flow out when the airplane is parked with the engine off. The fuel jet is located within a venturi. So the pressure in the venturi is lower than the ambient pressure by an amount that's based on the speed of the air that's flowing through that venturi. So the faster that the air is going through the venturi, the lower the pressure. The pressure driving fuel from the float chamber to the fuel valve is the difference between the ambient pressure and the pressure in the venturi. The float carburetor only works under positive G's. That's fine for most of us, but it's bad for people who want to do aerobatics in their airplanes. Float carburetors don't require the fuel to be pressurized. If the fuel tank are higher than the carburetor, then gravity causes the fuel to flow into the carburetor and you don't need any additional pumping. An alternative to a float carburetor is a pressure carburetor. They're sometimes called throttle body injectors. Pressure carburetors use a different mechanism for regulating the flow rate of the fuel, but the flow rate is still based on the pressure difference that's due to a venturi. Pressure carburetors require the fuel to be pressurized, but they do work with both positive and negative G's. As the air flows through the carburetor and the throttle, two things cause the temperature of the air to drop by as much as 60 degrees. First, as the fuel vaporizes or changes from liquid to gas, it absorbs heat. That decreases the temperature of the air. Secondly, as the air flows past the restriction caused by the throttle, especially if it's a nearly closed throttle, then pressure and density both drop. This is a form of adiabatic expansion, which causes a drop in temperature. If the temperature drops below the dew point, then any moisture in that air will condense. And if the temperature is also below the freezing point, then when it condenses, it will condense in the form of ice, which can end up in the venturi or it can end up around the throttle or both. Ice forming around the throttle will further restrict the airflow. It's like closing the throttle further. That causes a drop in power, and it causes ice to start forming even faster. Similarly, ice forming in the venturi will make that venturi opening even narrower, and it will cause more fuel to flow in, making a richer mixture, which can lead to even more carburetor icing. So, in other words, once ice starts to form, the problem is likely to get worse. There are certain conditions where carburetor icing is most likely to happen. First factor is temperature. It's most likely on temperatures between 20 degrees and 70 degrees Fahrenheit. If it's warmer than 70 degrees, then usually the air will not get cold enough to form ice. If it's less than 20 degrees, then usually there won't be enough humidity in the air to form ice. Those aren't absolutes. It's also relative humidity is important. It's much more likely to get carburetor ice if the relative humidity is higher than 60%. And your throttle setting makes a difference. A lot more likely to happen when the throttle is closed or nearly closed, or when you're operating at low power settings. Continental engines are more susceptible than Lycoming engines. Due to the location of the carburetor in Lycoming engines, the carburetor gets some heat from warm engine oil, which makes carburetor icing less likely. Some aircraft have carburetor temperature gauges, so you can look at whether the air is getting close to the freezing point, but in most aircraft, the only indication that carburetor ice is happening will be a gradual loss of power. To prevent carburetor ice, we use the carburetor heat whenever we're in situations where carburetor icing is likely. What the carburetor heat control does is it selects a different source for the intake air. It selects air that has passed through a heat exchanger and absorbed some heat from the exhaust air, so that warmer air will be going into the carburetor. When we're putting that warmer, less dense air into the carburetor, then the engine will develop less power. If carburetor ice is already there when you select carburetor heat, then the power will gradually increase after that initial drop as that ice melts away. However, the engine may run even a little rougher while it's clearing out that ice. Now, whenever you have a problem and you try something that seems to make that problem worse, human nature is to stop whatever you're doing and try something else. In the case of carburetor heat, you need to resist that temptation and be patient and give it time to work. The general rule is that you want to avoid using carburetor heat when you're on the ground, because that alternate source of air bypasses the air filter.
During run-up, we apply carburetor heat for a couple seconds and the engine speed drops. Does that confirm that we don't have any carburetor ice?
That confirms that the carburetor heat works. If we have reason to suspect that we might be developing ice, we need to leave the carburetor heat on for 10 to 15 seconds. If the engine speed starts to come back up during that time, then some carburetor ice had developed.
What would we do if carburetor ice was forming while we were taxiing?
We would want to apply carburetor heat just before takeoff for long enough that the engine speed stabilizes. Then we would remove carb heat for the takeoff.
Some aircraft engines use a fuel injection system instead of using a carburetor. One advantage of these fuel injection systems is that they mostly eliminate the risk of induction system icing. In a fuel injection system, a fuel pump pressurizes the fuel. There's usually an engine-driven primary fuel pump and an electrically driven boost pump. A fuel servo controls the flow rate. Like a carburetor, the flow rate is almost proportional to volume flow rate of air, but not proportional to density. Therefore, the mixture ratio won't change when you change the throttle setting, but it does change when your altitude changes. A flow divider distributes the flow to all of the different cylinders. One injector per cylinder sprays the fuel into the intake manifold very near the intake port. These injectors are much better than carburetors at achieving an equal air-fuel ratio among the cylinders. Starting procedures for engines with fuel injection may be different than for engines with carburetors, especially for hot starts. If you transition to an airplane that has fuel injection, that should be part of your checkout.
Wow. A lot happens to get the right amount of air and fuel into the cylinders.
Yes, the induction system is the part of the engine that the pilot has the most control over. You also need to understand the remaining engine systems. Next, we will talk about what causes the air and fuel mixture to burn once it is in the cylinders.
Aircraft engines have dual ignition systems. Each ignition system includes one spark plug in each cylinder, a magneto or electronic ignition unit, and an ignition harness. In addition to redundancy, dual ignition improves performance by speeding up combustion. Each magneto is driven by the crankshaft and gets all of its power from the crankshaft. The magnetos don't require any external electrical power. Now, a unique feature of a magneto is how it's turned on and off. Unlike a typical light switch, which gets turned on by making an electrical connection, a magneto is actually turned on by breaking an electrical connection. In order to turn the magneto off, a thing called the P-lead on the magneto has to be connected to ground, which happens via the ignition switch. If the ignition switch is turned off, that makes the connection. However, if that connection anywhere between the magneto and ground is broken for any other reason, such as a broken wire, then the magneto will be in the on condition. Some aircraft have a separate on-off switch for each magneto. In other aircraft, the magneto switches are part of the key. Since a magneto is powered by the engine, and the engine needs the magneto to be working to run, we have a bit of a chicken and egg problem when it comes to getting the engine started. During engine cranking, the engine doesn't turn fast enough for the magneto to produce a good quality spark. Even if it did produce a spark, the spark would happen too early and the fuel would be burning before the beginning of the power stroke. To deal with these problems, magnetos may be equipped with something called an impulse coupling. An impulse coupling winds up a spring until just after the beginning of the power stroke, then it releases the spring so that that magnet inside the magneto turns fast enough to produce a good spark, and it happens at the right time. Once the engine is turning fast enough to work without that, then there are some flyweights inside the impulse coupling that disable the impulse coupling's function, and it gets driven directly from the crankshaft. Many engines have an impulse coupling on only one of the two magnetos. Because of these impulse couplings, an aircraft does not need to be rotating very fast to start. So that fact, plus the possibility that the engine ignition might not actually be off when we think it is, that means we always need to be prepared for the engine to start whenever we turn the propeller even a little bit. The spark plug is what actually makes the spark. Each spark plug has a central electrode which is connected to the magneto by the ignition harness. The outer part is connected to ground. At least it's connected to the ground through the cylinders. It's usually also connected to ground through the ignition harness. These two parts are separated by an insulator through most of the spark plug. In the part that sticks into the cylinder, the two are separated by an air gap. When the magneto produces a high voltage, electricity arcs across that air gap. That is the spark that ignites the fuel and air mixture in the cylinder. For that to work correctly, the air gap needs to be an appropriate size. So checking and adjusting that gap is usually part of every annual inspection. If there's something besides air in the air gap, like lead deposits, then a spark might not happen. That's referred to as a fouled spark plug. Usually the cause of a fouled spark plug is running with the mixture too rich. Some aircraft have electronic ignition systems in place of one or both magneto-based systems. Electronic ignition systems, which are commonplace in modern cars, have a number of advantages over a magneto-based system. Electronic ignition produces a stronger spark than a magneto, and the timing of the spark can be adjusted based on engine speed so that combustion starts earlier when the engine's running fast. One disadvantage of electronic ignition is that it requires a separate source of electric power, like a battery. Normally, combustion starts when the spark plug fires, and then a flame front progresses from the spark plugs across the cylinder volume as that fuel gradually burns. Since that takes some time, the ignition system starts the process a little bit before the beginning of the power stroke. The fuel doesn't finish burning until slightly after the beginning of the power stroke. Pre-ignition is when something other than the spark plug firing starts the combustion process. One example would be, say, a small sliver of metal that gets hot during the power stroke and stays hot so that it ignites the mixture during the following compression stroke. Pre-ignition can lead to excessive cylinder pressures and excessive cylinder head temperatures. To resolve that problem, reducing power will reduce those symptoms. When we get to talking about the cooling system later, we'll discuss ways that you can improve cylinder cooling if a pre-ignition is happening. Detonation is when the compression itself causes the fuel mixture to explode as to burning gradually. Diesel engines are designed to have compression ignition, but gasoline engines are not designed for that. The extreme pressures that happen in cylinders can cause an engine to fail in minutes. The pistons can literally melt. The connecting rods are supposed to be straight. The connecting rod in this picture was straight before a detonation event vented. Detonation is most likely to happen when you have a high manifold pressure and low engine speed. Using lower octane fuel makes detonation more likely. It will show up on your engine gauges as a rapid increase in cylinder head temperature. If it happens, reducing power is the best way to resolve it. If you have a constant speed propeller, increasing engine speed will help to resolve detonation. The next system we'll cover is the exhaust system. The role of the exhaust system is to route the burned fuel and air mixture from the exhaust ports of the cylinders away from the aircraft. An aircraft exhaust system includes collectors. These are the parts that route the exhaust gas from the cylinders to the muffler itself, a shroud, which it's shown off to the side of the muffler in this diagram, but when it's installed, it goes over the top of the muffler and surrounds the muffler. Air gets routed between the muffler and the shroud, and that heats up the air to provide carburetor heat and also to provide cabin heat. And then finally, the tailpipe. The exhaust system geometry can vary quite a lot from one aircraft to another. In the aircraft that is pictured in this picture, there's a separate exhaust system for the left cylinders and the right cylinders. In other aircraft, all of the exhaust may be routed through a single muffler. This is a cutaway view of a car muffler, but aircraft mufflers work on the same principles. So the exhaust gases that come out of the cylinders in pulses. The pulses create loud sounds. The gas itself goes from the inlet pipe of the muffler to the outlet through perforations in those pipes. However, the sound waves tend to reflect off of walls within the muffler. The walls are spaced apart by carefully calculated distances so that the reflected waves are out of phase with the original sound wave, which causes them to cancel each other out and the sound to be much quieter. Mufflers do impede the flow of exhaust gas somewhat. That reduces power. Some aircraft have systems called tuned exhaust systems. In these systems, the length of each of the collectors is carefully calculated so that the flow from one cylinder creates a slight vacuum just as the next cylinder is ready to release its exhaust. These tuned exhaust systems have a lot less back pressure, and that improves the performance of the engine. One thing that can go wrong in an exhaust system is that some of the parts can develop leaks. The first indication of a leak is a tan-colored discoloration around the leak. So that's something that you should look for during your pre-flight inspection on all of the exhaust system parts that you can see during the inspection. Leaks in the muffler are particularly problematic because, for one thing, it's hard to see them because they're covered up by the shroud, and also they can allow carbon monoxide to get into the cabin because that's where the cabin heat comes from.
Carbon monoxide in the cockpit would really ruin our day. I'm sure glad that we have a good carbon monoxide detector in the cabin.
Next, we'll talk about the lubrication system. Lubrication is provided by engine oil. The manufacturer specifies what types of oil may be used and what quantity is required. During pre-flight, the pilot should verify the quantity using the dipstick. This is a schematic diagram of an engine lubrication system. An engine-driven pump draws oil from the sump and pressurizes it. Large particles are filtered out by a screen upstream of the pump, and finer particles are filtered out by an oil filter downstream of the pump. During oil changes, the filter may be cut open and inspected. The particles that are found in the filter can be an early indication of an impending problem. The pressurized oil is routed to various parts of the engine that need lubrication. From there, it drains back to the sump. Some engines have a dry sump lubrication system in which the oil is transferred to a separate oil tank instead of collecting in the bottom of the crankcase. The oil may flow through an oil cooler to reduce the oil temperature. In some aircraft, a thermostat automatically bypasses the oil cooler when the oil is not up to temperature. Some aircraft have a winterization kit that blocks airflow through the oil cooler, allowing the oil to warm up enough in the wintertime. Whenever the engine is off, water vapor can condense inside the engine, leading to water in the oil. As the oil heats up, that water in the oil evaporates and exits through this breather tube. If the oil doesn't get hot enough to evaporate the water may lead to corrosion inside the engine. Oil temperature gauges and oil pressure gauges tell the pilot if the system is functioning properly.
The oil pressure and oil temperature are both in the green now. If the readings weren't in the green, what would that mean? And what should I do about it?
First, let's consider a low oil temperature with a normal oil pressure. This is the normal condition right after you start up and while you're operating at low power. It takes a little while for the oil temperature to come up into its normal range. If the oil temperature doesn't get warm enough, even during cruise, then condensation in the oil won't be evaporating and leaving the oil. That makes the oil less effective. That's not an urgent situation, but it is something that's worth discussing with your mechanic after the flight. High oil temperature with normal oil pressure generally means that your engine's starting to get too hot. So you need to do the things that will help cool the engine better, as we'll discuss in the next section. Consider reducing the engine power setting, consider enriching the mixture, or increasing the airspeed by adjusting your pitch attitude. Sometimes this can be an indication that the oil quantity is lower than it should be. The really serious situation is when we have low oil pressure. When we have low oil pressure combined with normal oil temperature, that might be a faulty oil pressure gauge, or it may be caused by an oil leak that's ongoing. While you're busy hoping that it's a faulty gauge, you should be preparing for the situation that it may be a real oil leak. If that's the case, then things are going to be getting worse. The oil temperature will start to increase rapidly as that oil quantity decreases. Since you're not sure how much longer you can expect to continue having engine power, you need to start planning for an emergency landing. That means you need to look around, find places where you could safely put the airplane down, and fly to that location. Once you're at that location, you can think about how you could get to an airport, but don't fly away from your place that you could safely land in a field unless you are in gliding distance of another place that you could safely land. If you have low oil pressure combined with high oil temperature, then you can stop hoping that it's a oil pressure gauge problem. The situation is going to get worse, and it's going to start getting worse quickly. You should expect not to have engine power very much longer and start planning for an emergency landing that will be happening soon. Some aircraft are equipped with engine monitors that provide much more information than the standard set of engine gauges. Engine monitors usually measure the cylinder head temperature and the exhaust gas temperature for every cylinder, as opposed to only measuring it for one. This makes it much easier to detect if a problem like pre-ignition, detonation, or a fouled spark plug is occurring in one cylinder. Engine monitors have alarm set points to get the pilot's attention when any parameter is out of range. Whenever you report an issue to your mechanic, it'll be common for the mechanic to ask questions about various engine gauge readings that were leading up to the issue and during the issue. But as pilots, we have a lot of other things that we're thinking about whenever we're dealing with an engine issue, so we frequently don't remember what these readings were. Engine monitors record the engine data at frequent intervals, so that data can be analyzed after the flight and shared with your mechanic. Only about 1/3 of the energy of combustion ends up driving the propeller. The remainder gets converted to heat. That heat needs to be dissipated so the engine components don't get too hot. A large portion of that waste heat gets ejected through the exhaust gases. A rich mixture increases the heat capacity of that exhaust gas. The extra fuel sort of acts as a heat sink for all that heat. The way the remaining heat gets dissipated is mainly through cooling fins around the cylinders. In a typical horizontally opposed engine installation, air flows into the front of the cowling, then it flows downward past the cylinder fins and out the bottom of the cowling. There's baffling in the engine compartment that forces the air to flow past the cylinder fins. Some engines, like the Rotax 900 series, also have liquid cooling of some of the engine parts. And some heat gets absorbed by the oil and then ejected through the oil cooler. The most challenging time to keep the engine cool is during climb, because the engine is generating a lot of power and a lot of heat, and the airspeed, which helps with cooling, is low. To help with that, some aircraft have pilot-controlled cowl flaps, which increase the airflow when they're open and reduce the drag when they're closed. Our final topic in this lesson is the propeller. The propeller converts rotational motion generated by the engine into forward thrust force. In training airplanes, the most common type of propeller is a fixed pitch propeller, as shown here. The propeller blades are airfoil shaped, like the wings. The blades strike the air with an angle of attack to generate a thrust force, in the same way that a wing produces a lift force. Since the propeller tips follow a larger arc than the inner parts of the blades are twisted so that each part has close to the same angle of attack. A fixed pitch propeller is characterized by three numbers: the number of blades, the diameter, and the pitch. Pitch is how far forward the airplane would need to move per propeller revolution in order for the blades to have a zero angle of attack. For maximum takeoff and climb performance, a shallow pitch is better, which would mean a low number for the pitch. However, a propeller that's optimized for climb airspeed will not have enough of an angle of attack at cruise speed to generate a high thrust force unless the engine's turning very fast, and engines usually have limits on how fast they're allowed to turn. For maximum cruise performance, on the other hand, a steep pitch is best, meaning a high pitch number. However, a cruise propeller will resist rotation at slow speed, and it'll prevent the engine from turning as fast as the engine needs to in order to generate high power. So a blade pitch that's a compromise is typically what is chosen. Usually the propeller is bolted to a flange at the front of the crankshaft. Some engines, like the Rotax 900 series, have gearing so that the propeller can spin slower than what the engine is. There may be a spinner over the hub, which reduces drag a little bit and generally makes the airplane look better. A variable pitch propeller reduces the need to compromise between climb performance and cruise performance. The blades rotate with respect to the hub to make the pitch flatter for better low-speed thrust, or coarser for better high-speed efficiency. Some propellers are ground adjustable, which means that the pitch can only be changed between flights with the engine off. So you still need to select a compromised pitch, but you can change how you weigh that compromise based on your mission. If you're flying long distances using airports with long runways and no obstructions, then you can set the pitch high. Then if you're later operating from a short runway where takeoff performance is real critical, then you can change it to a low pitch while you're doing that. In-flight adjustable propellers usually utilize hydraulic pressure, which is routed through the crankshaft to the propeller hub in order to change the pitch. The most common way that this gets controlled is a propeller knob in the cockpit that the pilot uses to set the engine speed. From that, a governor adjusts the pitch of the propeller to achieve that speed. That's called a constant speed propeller.
I know that was a lot of material to learn. In addition to knowing how each engine system is supposed to work, we also talked about some of the things that can go wrong, like carburetor icing, accidentally hot mags, pre-ignition, detonation, exhaust leaks, and oil leaks. We talked about how to prevent these problems, how to recognize them if they happen, and what to do about them if they happen.